Yes, we can.
Okay.
Yes.
So finding inverse Laplace transform using complex numbers. So to appreciate the concept of finding inverse transform by complex numbers, we'll solve the same problems we solved last week by using concept of partial fractions and completing squares. So demonstrate by an example. Find the inverse Laplace transform of the following find the inverse Laplace transform of the following functions using concept of complex numbers. So the first problem, we have s plus 3 divided by s squared plus 6s plus 13. And b, we have 2s plus 3 over s squared plus 6s plus 13. And remember, a complex number is any number of the form a plus bi. So where I is the square root of -1. So that's the question. So first step is to factorize the denominator as a product of linear terms. To factorize the denominator as a product of linear functions of s. But now to do that, we try to solve this equation. So we try to find the zeros of this denominator, which by quadratic formula will give us -6 plus or minus square root of 36 minus 4 times 13 divided by 2. So which is -6 plus or minus square root of -16 divided by 2. So s would be -6 plus or minus 4i divided by 2, which is minus 3 plus or minus 2i. So remember, square root of minus 16 is the same as square root of 16 times square root of minus 1. So plus or minus 4, square root of minus 1 is I. So this means that you can write the denominator as a product of two linear terms, s minus a times s minus b, where a is the negative 3 plus 2i and b negative 3 minus 2i. So this means that the denominator can be factored as s squared plus 6s plus 13 is the same as s minus a times s minus b, where a can be taken to be the first root, minus 3 plus 2i, and b to be taken as minus 3 minus 2i. So then now, since now you have written the quadratic expression as a product of two linear terms, we can use the concept of partial fractions to easily find the inverse transform. So now we use partial fractions i.e., we have the problem s plus 3 divided by s squared plus 6s plus 13, which we are saying that the denominator can be written as s minus a, s minus b. So if you carry out partial fraction decomposition, we'll get these two fractions. So where capital A and small a, capital A and capital B are unknown constants to be found. So A and B are to be found. Now you know that if we have s plus 3 over s minus a times s minus b, then we put the right hand side over same LCM, s minus a times s minus b. So this will be a into s minus b plus b into s minus a. That's the usual way of partial fraction decomposition. What would be the meaning of that equation?
The top is equal to s plus 3.
Yes, so the top, because the denominators are the same. So s plus 3 is the same as a into s minus b plus b into s minus a. So we can say when s is given by a, we can solve for capital A, okay? when S is small a, we can solve for capital A. So this implies that we'll have small a plus 3 equals to a into small a minus b, but this part will not be there because a minus a is 0 times b, 0. So which means, but a itself was given by minus 3 plus 2i, so equals to a into minus 3 plus 2i. B is minus 3 minus 2i. So this will be 2i equals to a into minus 3 plus 2i plus 3 plus 2i. So what will be the simplification of the bracket on the right hand side?
For I.
4i, correct. So therefore, this implies 2i equals to 4ai. And then this means that 2 should be the same as 4a. So which means a is what?
One over two.
A is a
1
half.
over 2. Yeah, so a is a half. So that means that a is a half. Now to get capital B, we fix small a, we fix S to B. How do you find capital B? What should we fix for S for us to have B value?
B.
Small b, correct. Because when you fix S to be small b, or they will not have this part because b minus b is 0. So this will imply that b plus 3 equals to capital B, B minus A. But B is the same as minus 3 minus 2i equals to B into minus 3 minus 2i. A is minus 3 plus 2i. So I'll have minus 2i equals to B into minus 3 minus 2i plus 3 minus 2i. So what is the simplification of the bracket?
Minus 4i.
Minus 4i. So this means that we have minus 2i equals to minus 4bi. It's not hard to see that b is also a half. So therefore now we have s plus 3 over s squared plus 6s plus 13 will be now a half over s minus a plus a half over s minus b. So now taking inverse Laplace transform, we find that the inverse Laplace transform of s plus 3 over s squared plus 6s plus 13 will be the inverse of a half s minus a plus inverse of a half s minus b. And then by linearity property, you can say this a half inverse of 1 over s minus a plus a half inverse of 1 over s minus b. Now, then you go back to your Laplace transform table and tell me what is the inverse of 1 over s minus a?
E raised to power 80.
Right. So e raised to power 80. And then 1 over s minus b.
E raised to power bt.
E raised to power bt, correct. So which you can as well write as a half into e raised to power at plus e raised to power bt. But you see, we have a is the same as minus 3 plus 2i. And then b is the same as minus 3 minus 2i. That's by definition. Then using this, will have a half into e raised power minus 3t plus 2ti plus e raised power minus 3t minus 2ti. So it's a game of playing with the properties of exponents. So this will be a half into e raised power negative 3t, e raised power 2ti plus e raised power negative 3t, e raised power negative 2ti. So remember, I'm using the property that e raised power a plus b is the same as e raised power a times e raised power b.
Excuse.
Yep.
The last part it will be
The last?
in the last part it will be e power negative 3t over.
Okay, so there's no problem. It's still the same. So remember, when I write minus 3t minus 2ti, the same as minus 3t plus minus 2ti. So if you put over, then you'll have now positive 2ti. There's no problem if you make it positive. Okay.
Okay.
Yeah. So and so we can say, so common here is e raised to power minus 3t. So we can say this a half e raised to power minus 3t into e raised to power 2ti plus e raised to power minus 2ti. But then we know from our pure mathematics, De Moivre's theorem states that e raised to power theta I is the same as this Euler's identity gives us cosine of theta plus I sine theta. This Euler's identity. So the Euler's identity is going to help us to rewrite what we have in the square brackets. So the role of theta will be taken by 2t here, and then here will be minus 2t. So which means e raised power 2ti will be the same as cosine of 2t plus I sine 2t, while e raised power negative 2ti will be cosine of 2t minus I sine 2t. So if I add these two, What do I get?
Two cos
I
2t.
2
Cos
cosine of
2t.
2t. Yes, so that's the sum. So it means this bracket is nothing but twice cosine of 2t. So if you simplify, a half and 2 will cancel out. So we'll get e raised to power minus 3t and then cosine of 2t. If you check it, the same answer that we obtained by concept of completing the square. So the reason that's why we give this many different ways of solving a problem. Sometimes one way might be easier than the other way. So if you know all of them, so it's always good to know how to solve a problem in many ways. So that's what we get. E raised power minus 3t cosine of 2t. And then part B, we had to find the inverse Laplace transform of 2s plus 3 divided by s squared plus 6s plus 13. And because the denominator has the same structure as the previous problem in A, so we are free to say that this is the same as the inverse transform of 2s plus 3 over s minus a times s minus b. So I'm doing this because already we have shown how to decompose the denominator into product of linear terms. If it was a different quadratic, then you have to go through the same steps. And this will be the inverse of capital A over small a minus small a plus capital B s minus b. So the process of partial fraction decomposition for this expression. So which is the same as the inverse transform of A over S minus A plus the inverse transform of B over S minus B. But now remember here, the capital A and small capital A and capital B may not necessarily be the same values as what you have done previously, because we have 2s plus 3 over s minus a, s minus b is the same as capital A over small s minus a plus b over s minus a. Don't forget that because we have the same quadratic, then the small a still is minus 3 plus 2i, and small b is minus 3 minus 2i. So these remain the same values because we are dealing with the same quadratic expression. So this is 2s plus 3 s minus a, s minus b, a into s minus, so this is b, minus b plus b into s minus a, everything divided by s minus a, s minus b. This will mean that 2s plus 3 equals to a into s minus b plus b into s minus a. So let s be small a. So when you say s to be small a, I not have the capital B term, So I'll be able to solve small capital A. So this will imply that 2A plus 3 is capital A. So it will be 2 into minus 3 plus 2I plus 3 is A into minus 3 plus 2I minus 3 minus 2I. So minus 6 plus 4I plus 3 equals to A into minus 3 plus 2I plus 3 plus 2I. So what do we get inside the brackets?
Four I.
4I. Because we will minus 3 and 3 cancel, so we'll have 4AI. Then this other side will have minus 3 plus 4I. So to get the value of A, then the imaginary parts must agree. So we have, okay, so simply to get A here, so it's like we are dividing both sides by 4I. So A will be minus 3 plus 4I. Then you multiply by the conjugate of this, which is minus 4I, divided by 4I times minus 4I. So we'll have 4I times minus 4I. What, Ben?
I.
Sure.
16.
So the 16, because we'll have negative I squared, which is, remember, I squared is -1. So negative I squared is the same as -1 times -1, so +1. Then 4 by 4 is 16, so we have 16. So minus is plus, so I will have 16 and then minus. Is it minus or plus?
It's plus.
Plus. So that will give us 12I. So which finally, if you divide everything by 16, we'll have A will be the same as 1 plus 12 over 16.
3 over 4.
3 over 4, which is the same as 0.75I. And then when S is small b, so we'll have 2b plus 3 equals to capital B into B minus A. So we'll have, okay, so this will be now 2S is the same as 2B. So this will be 2B. So that will give us, so 2B. So which means 2 into minus 3 minus 2I plus 3 is capital B into minus 3 minus 2I minus 3 plus 2i, values of small and small b. So this will give us minus 6 minus 4i plus 3 equals to b into minus 3 minus 2i plus 3 minus 2i. So what do we have in the brackets?
For BI.
Minus 4i, okay?
Yeah.
Yeah, equals to, so minus 3 minus 4i. So also to get b, you divide through by minus 4i. So this means that b would be minus 3 minus 4i divided by minus 4i. Now you simplify this by multiplying each by conjugate of the denominator. So which will give us minus 16 and then minus 12i over 16. Is it so? Positive 16, this is not minus. Positive 16 plus minus 12i over 16. So which means b is 1 minus 0.75i. So this now to say the original expression 2s plus 3 over s squared plus 6s plus 13 will be the same as 2s plus 3 over s minus a, s minus b is the same as capital A over s minus a plus b over s minus b. But then our a is 1 plus 0.75i over s minus a, and our b is 1 minus 0.75i divided by s minus b. So we do now the usual process. Supply inverse Laplace transform on both sides, which means that inverse Laplace transform of 2s plus 3 s squared plus 6s plus 13 will be the inverse Laplace transform of 1 plus 0.75i over s minus a plus inverse transform of 1 and then divided by s minus b. So remember the numerator 1 plus 0.75i and 1 minus 0.7i, they're just constant. So linearity property allows it to be factored out. So this will be 1 plus 0.75i, the inverse transform of 1 over s minus a plus 1 minus 0.75i inverse of 1 over s minus b. And we have just found out that the inverse transform of 1 over s minus a is e raised to power a t this other one is e raised power bt. But remember, A and B are just our own creation. So our their respective values are e raised power -3 plus 2i t plus 1 minus 0.75 I times e raised power -3 minus 2i t. That's by definition of A and B. So you also play with the exponentials. So we'll have 1 plus 0.75 I e raised power -3t e raised power 2 ti e raised power -3t e raised power -2ti. Then using Euler's identity, you can now transform the exponentials involving the imaginary unit in terms of cosine and sine. So which will be 1 plus 0.75 I e raised power -3t cosine of 2t plus I sine 2t plus 1 minus 0.75 I e raised power -3t into cosine of 2t minus I sine of 2t. In fact, e raised power -3t is common. So I have 1 plus 0.7 I cosine of 2t plus I sine of 2t plus 1 minus 0.75 I cosine of 2t minus I sine of 2t. Because I'm lazy, I'm not going to do all those expansions, but check to see that you'll get e raised power -3t into twice cosine of 2t minus 1.5 sine of 2t. If you open the bracket and simplify, you'll end up with that as the final answer. So 5 minutes break, and then we come to finish up on the convolution theorem and how to find solution of differential equations by Laplace transforms.